Welcome back, ladies and gentlemen. In this video, we're looking at the connection between work and energy. You've learned that energy is the ability of an object to change something about itself or about the world around it, some quality or some property that an object can have that allows it to make that change. You've also learned that work is something done to an object that will change something about that object. So basically, it's going to change the motion of the object. But more specifically, it's going to, there's a connection. It's going to change the energy, and we'll see that. So, for example, you might have an object, and you're going to apply a force to that object, and the object will move. All right. So, what do we have going on here? While the object moves, you've got your displacement. The force is continuously applied to the object all the way across. The force isn't just a one-time thing over here. It's applied the whole way. For example, we get Seamus going on the skateboard here, and we're going to apply a force to this, and okay, I kind of missed. I could probably do better. So, all right, so what did you see? You saw Seamus move, but also, more importantly, you saw the motion changing, and that's what's going on here. So we had an initial velocity going on here, and we had a final velocity over here. Now this kind of looks like something kinematics related. What do we have? So there is a displacement going on. There is this initial velocity. There is this final velocity. Now it's almost like if we had one more thing, well we have a force here, but if we had one more thing, we might easily recognize a particular kinematics equation, right? Displacement, initial, final velocity. Let's see. Well, I happen to recall this one, where the final velocity squared equals the initial velocity squared plus 2 times acceleration times the displacement. All right. And now, remember, I have this force up here is also part of what's going on, so I'm going to list that. And but force isn't in this equation. So what do I do? Oh, I remember something. There's a connection. There's a link between force and acceleration, isn't there? Newton's second law, right? Newton's second law says that force equals mass times acceleration, or if I rearrange that, acceleration equals force divided by mass. Okay. Does that object have some mass? Yes, it does. Are we applying a force to it? Yes, we are. So we have that going on. What I can do is rewrite that and make a substitution. You have to be patient with me, stay with me on this. Just a little bit of math, algebra, moving things around in an equation, and you're going to see something kind of cool. So the substitution, I'm just going to, instead of write A, I'm going to write force divided by mass, because that equals acceleration. So here we go. Just rewriting, that's all I'm doing here. Same equation. And at this point is where I'm going to make that substitution. Instead of writing acceleration, I'm going to write force divided by mass. And there's my displacement at the end. Same equation, that little tiny change there. And this is going to be, it's going to turn into something kind of interesting. Now, there's something else here too. That displacement right there. Well, if we're trying to make a connection between work and energy, the equation for work doesn't use a delta x for displacement, it uses a d for distance. So what if I change that? I'm going to write a d instead of the delta x right there. It's going to be the same thing. It means the same thing. So I'm going to do one more rewrite of this equation, putting a d in there instead. And let's see what this ends up looking like. We've got this final velocity. Still writing the equation, same equation, equals initial velocity squared plus 2 times, remember, force divided by mass. That's the same as acceleration. Oh, I said acceleration and then wrote it accidentally. Mass. Sorry. Oops. Okay. And but now instead of delta x, I'm going to write a d. There. And now here's something that you should try to see. In this equation, you should see 2 things that look familiar related to work. And those 2 things, if you remember the equation for work is force times distance times cosine of the angle theta. Well, what we have here is a force and a distance. right there. We have a force times distance. So what I'm going to do is I'm actually going to isolate F and D and get those together on one side of the equal sign and get them all by themselves. So when you're doing this kind of algebra, you're going to want to follow the same kind of rules of rearranging equations we've used before. So start working your way from outside in. This is what we have to get rid of first. We have to subtract initial velocity squared from both sides. And so here we're going to have final velocity squared minus initial velocity squared, because on this side it canceled out. And now we're going to have 2 times force times distance, and remember we're dividing by mass. So force times distance divided by mass. And I have I can do this in one more step. I have to divide both sides by 2, and I have to multiply both sides by m. Well, instead of divided by 2, what if I multiplied by 1/2? So I'm going to multiply by 1/2, and that'll cancel out the multiply by 2. So I'll have to do the same thing over here. Multiply by 1/2, and I have to multiply both sides by m to cancel that over here. So m and m, okay. And just like this canceled here, the 1/2 cancels the 2. Multiplying by m cancels dividing by m, right? And so let me rewrite this kind of as neat as I can. I've got 1/2. Let me kind of separate what's going on here. 1/2, and I got an m. Why did I switch them? There's no particular reason. It doesn't. The order doesn't matter. And I'm multiplying by v final squared. That's final velocity squared minus initial velocity squared. Multiplying by that chunk right there. And over here, what do I have left? I've got force times distance, FD. And so hopefully you recognize what's going on here on this side. This is essentially the work done on the object. Now, we were using an equation from kinematics, and that's interesting, but right, in kinematics, oftentimes the velocity is changing, the motion is changing. Okay, that must mean work is done, and that's true. Work was done. Now, what's going on this side? Well, I see clearly something's changing, right? There's an initial and a final, and mass is involved, and I've got this 1/2 sitting out over here. Okay, we're connecting work to energy. What kind of energy are we talking about? The energy of motion, kinetic energy. And this is kind of looking like it might be kinetic energy. Look, if I hide that, I've got 1/2 mv squared. If I hide that one, I've got 1/2 mv squared. Different v's going on, right? Well, what I can do mathematically is I can distribute 1/2 m times vf squared, and I'll have 1/2 m, excuse me, times vi squared. You'll see what this looks like, 1/2 m vf times vf squared. And there's a minus sign that comes from right here. And I'm going to have 1/2 m times vi squared. And I've got to keep this force times distance on that side. So this is the interesting part. Look what I've got. I've got 1/2 mv final squared and 1/2 mv initial squared. This is the initial kinetic energy. Yeah, I know it was the initial velocity, but when you look at it this way, you've got the 1/2 m times that velocity squared. Well, that is an initial kinetic energy. And this is 1/2 mv final squared. This is a final kinetic energy. And this is a force times a distance. Okay. Well, I could really stop writing force times distance, couldn't I? I could write work, the work done. I know there's no cosine theta, but okay, don't worry about that right now. Force times distance is the work done. Well, what's this? I've got a final minus an initial. Final minus initial, whenever you see that, it's a change in that thing. So I've got a change in the kinetic energy. And this right here, what we have found, now we'll really never have to do all this math again, but I like showing you how you get from A to B. What we have found is the connection between work and energy. this right here is called the work-energy theorem. It's got a name. It's pretty important. The work-energy theorem. It's a mathematical relationship between the amount of work done and the change in the kinetic energy of the object that's having work done to it. Okay, so a fair bit of math. You certainly don't have to memorize how the math was done, but I wanted to show you and help you follow along. When we apply a force to an object and the object moves through a distance, we're doing work on the object. Okay, that's real important to remember. When we do work on the object, we end up changing the kinetic energy of the object. That's also important to remember. So the conceptual understanding that's taking place. Remember what we did with Seamus on the skateboard, and we changed his kinetic energy. I can get him set up again a little bit. He's not fond of skateboards, but so we applied that force, and we ended up changing his kinetic energy. He went faster. All right. Oh, there he is. Well, that's it for now. Thanks for watching. This was the connection between work and energy, the work-energy theorem. Thanks for watching. I'll catch you next time.